We continue our ring theory exercises with this one. Next 30. So here it's given that in some ring, for every element x to the power n is equal to x, where n is some positive integer greater than 1. Then if this happens, and additionally we are able to find some ring element A whose mth power is equal to 0, where m is some positive integer, then we have to prove that that element A must be equal to 0. Now, using this condition and induction, we are going to first prove something more general than this. We claim that x to the power n to the power k is also equal to x for all ring elements x and all positive integers k. Okay. To establish this, we apply induction on k. When k is equal to 1, the equation is equal to x to the power n to the power k equal to x becomes just this, which is our which is given. So this forms the basis for our induction. Assume this for some positive integer k, and keep in mind that in this assumption that part is also included, that this equation, besides being true for that some positive integer k, is also true for any x, any element x in the ring. That thing is there, that is a part of the assumption, although we are not mentioning it explicitly. Then what is this? N to the power k plus 1. This is n to the power k times n. Now, because everything is a positive integer, n and k are positive integers, so n to the power k and n are positive integers. So that is why this integral power equals this. Now, by the induction hypothesis, the thing inside this power equals x, and by what is given, this condition, this is again equal to x. This completes the induction. And establishes our claim. Okay. Now we come to the actual solution. We want to prove that if this is true, then a must be equal to 0. Since n is greater than 1, we can choose a positive integer k sufficiently large such that n to the power k is greater than m. If n is equal to 1, this is not possible. I mean, unless m is, then also this is not possible because we are considering strict inequality. But because n is greater than 1, this is possible because if you take higher and higher values of k, the powers will increase. N to the power k will increase and it will overshoot m. It will go, at one point it will go beyond m. Whatever m is, no matter how large it is, n to the power k will go beyond it. Now, a can be written as a to the power n to the power k. Why? That is because we have proved this thing. No, this is our claim that for any element x in the ring, x to the power n to the power k is the element itself, no matter whatever k is. For all k and all x, this is possible. So in place of x we have now taken a, and in place of k, that particular k we are taking. Now this n to the power k can be written as n to the power k minus m plus m. That we are just simply adding and subtracting m, that's all. But now because n to the power k is strictly greater than m, n to the power k minus m is a positive integer and m is already a positive integer. So times a to the power m. Note that we are, although we are not saying it explicitly, but it seems like we are using rules of exponents which are available in groups. Yes, we are using such rules, but under the multiplication binary operation, a ring is not necessarily a group. And in fact, it is never a group. The non-zero elements in a ring are sometimes grouped, namely if the ring is a division ring. Okay, but still, in spite of not being a group, with respect to multiplication also, such rules of exponents are true, as long as you keep in mind that the exponent that you have, it stays positive. It stays a positive integer, it does not become negative, and that is because powers with negative exponent in a ring are not always meaningful, because inverses may not exist under multiplication. But here we don't have those problems because the exponents here are both positive integers, and that is why we have gone through this much trouble to make sure that we can find such an n to the power k which becomes greater than m. So now this of course stays as it is, and using this condition we can write the second factor as 0. So this becomes 0. So that's how a is 0. This completes the solution. Next, just give me a moment, okay? Again it has started lightning outside. Okay, so now exercise 31. It already rained quite heavily about an hour ago. Now again I think it will rain. Give an example of a ring. Give an example of ring elements. A and B. With the properties that AB is 0 but BA is not 0. And such an example can be quite easily found among the matrix rings. So we consider this. A is the 2 by 2 matrix, 0 0 0 1, and B is the 2 by 2 matrix, 0 1 0 0 in the ring of 2 by 2 matrices over the field of real numbers. Or if you want, you can take the ring of integers here also, because after all the entries we are considering are integers. Then what do we want? We want AB to be 0. Let us calculate AB. 0 0 0 1 0 plus 0 0 0 plus 0 0 0 plus again 0 0, finally this plus this again 0. So AB is 0, is the 0 matrix. But what about BA? 0 plus 0, 0, 0 plus 1. You see this first row second column entry becomes 1. 0 times 0 is 0 plus 1 times 1 is 1. And this of course this comes from the second row, which is entirely 0. So the other entries are 0. So AB is 0 but BA is non-zero. 32. Let n be an integer greater than 1. In a ring in which the nth power of x equals x for all x. Show that AB equal to 0 implies that BA is also equal to 0. So what we are getting here is not possible in a ring if this condition is true. And keep in mind here n has to be greater than 1, because for n equal to 1 this is trivially true in any ring. So combining this one and this one, we can say that in this ring, in this matrix ring, this condition is not true. Okay, such a positive integer n greater than 1 cannot be found such that all the nth powers are equal to the element itself. So AB is given to be 0. We want to prove that BA is 0. We immediately make use of this condition. This is BA to the power n. And BA to the power n becomes B times AB to the power n minus 1 times A. Note that n is greater than 1. What is this equality? What is this last step? We can understand that with say two simple examples. The smallest possible value of n can be 2. In this case, BA square means what? BA, and this BA actually, if you look at it closely, is AB to the power 2 minus 1 A. That's how we are getting this. We can see another one, BA, and here you can see that you are getting two ABs. So this is B AB square, and square is 3 minus 1 A. So that's how we are getting this, and we are also keeping in mind that n is greater than 1. If n is not greater than 1, then of course you cannot write like this. You can if the ring has a unity 1, because in that case this will become the 0th power of AB, which can be defined to be 1. But anyway, we get something like this, where the important point is that AB is there, okay, and that's why we are writing n is greater than 1. Here we have AB, here we have two ABs, so the presence of AB is important. Since AB is equal to 0, we thus have B0A equal to 0. So that's how BA is also 0. Next exercise 33. Suppose that R is a ring such that x cube is equal to x for all x in R. Prove that. Oh, so this time the rain is not just simply rain, it's a hailstorm. That too, the chunks are quite big, I think. Prove that six x is equal to 0 for all x in R. What's the harm in writing like this? I don't understand this with Gallian. For any x belonging to R, we have x plus x, that is 2x, is equal to x plus x whole cube by the given condition. Now what we will do, we will multiply the things out here. first if we multiply these two, we will get what? X square. Throughout we are getting x square. How many x squares? 1, 2, 3, 4. So and then again we multiply. After performing this multiplication, all we will get are x cubes, and how many? 4 plus 4, 8 x cubes we will get. So which of course we can write for the sake of simplicity as 8x cube, but then again because of this condition, this is nothing but 8x, and here we have 2 x's on that side, thus cancelling those 2 x's from both sides, we get 6x equal to 0. And keep in mind that this cancellation is possible because we are cancelling in the group in the ring under addition. The ring is a group under addition, so in that group we are applying the cancellation laws and we are getting this. Suppose that A belongs to a ring. Unnecessarily this much has to be written. You just in the beginning of a ring exercise you can write something like this. In the following exercises, R is a ring, that's it. Then you can write, suppose A belongs to R. You don't have to write such a long line again and again. Suppose that A belongs to a ring such that the fourth power of A is equal to the square of A. Prove that A to the power 2n is equal to also A square for all positive integers in. This naturally will we have to proceed by induction. So I will not write the formal things, I will just show you how the proof goes, which is almost trivial. You see, when you take n equal to 1, what happens to this equation? This equation becomes this, which is trivially true. So for n equal to 1, our claim is true. That is the basis for our induction. Suppose that this is true for some positive integer, and that is our induction hypothesis. That is, let this be true for some positive integer n. Then we perform the induction step in which we take n plus 1 in place of n. In that step, we will have this. So which is 2n plus 2. 2n is a positive integer, 2 is a positive integer, so it is this. Now a to the power 2n by our induction hypothesis is a square. So we get a square times a square, which is a to the power 4, which again is a square. So this completes the induction and proves our claim. Find an integer n greater than 1 such that a to the power n is equal to a for all a in set 6. Do the same for set 10. Okay, what else? Show that no such n exists. Or set m or Cm when m is divisible by the square of a prime, square of some prime. In set 6, these things are true. 1 cube is 1, of course. 2 cube is 8, but since we are in modulo 6, so 8 is equal to 2. So 3 cube is 3, like that. 4 cube is 64. 64 is 10 times 6 plus 4, that is equal to 4. So that means for Z6 or Z6, that n is 3. That's what we have guessed. We still have two more or only one more power to check. and this becomes what? If one divides this by 6, 125 is 120 plus 5, so that means 20 times 6 plus 5, so this is equal to 5. In this one is 10. So here that n value is 5. There are other n's also that you can find, but 5 works. So we want only one. This is 32. Now in this case, because our modulus is 10, so you just have to look at the first, the units place digit. 30 plus 2, 30 is divisible by 10, so this is 2. Three to the power 5 is 243. Modulo 10, that is 3. 4 to the power 5 is what? 1024. That is 4. Units digit is 4. Here units digit of course will be 5. 3125. 6 to the power 5. We have 10 modulus, so we have to go till 9. 6 to the power 5 is 7776. So that is 6. 7 to the power 5 is 16807. So that is equal to 7. 8 to the power 5 is 32768. That is equal to 8. And finally 9 to the power 5 is 59049. That is equal to 9. So in Z10 our n value is 5. Okay, now we come to the question of this thing not happening in Zm if m is divisible by the square of some prime. Note that these moduli 6, they are square free. An integer is square free if it is not divisible by the square of any prime. So 6 I need in here. Just give me a moment. A terrible storm is raging outside. Six is 2 times 3. Like that, 10 is 2 times 5. None of them is divisible by the square of any prime, whereas 12 is 2 square times 3, or 24 is 2 cube times 3. These are square free numbers. These are not square free. This is divisible by 2 square. This is also divisible by 2 square. So if some prime can be found whose square divides an integer, that integer is not square free. Square free integers look like this. If you multiply this by 3, getting 30, 30 is also a square free integer. So for square free moduli, we have found that such n's exist. Now if there is if it is not square free, then we have to prove that this cannot happen. Okay, let P be a prime such that m is equal to p square times t, where t is some positive integer. Then this number pt, this belongs to Zn. Why? Because pt is strictly less than p square t. That is because p being a prime is greater than 1, and also because p and t are both positive integers, so this is greater than or equal to 1. In fact, it is strictly greater than 1. pt lies between 1 and m, like this. The reason this is strictly greater than 1 is because p itself is greater than 1, and the reason this is strictly less than m is that p have another p. I mean, if we want to have m, we have to multiply this by p. So that means this belongs to Zm, and suppose there exists an integer n greater than 1. So now we are going to suppose the thing that we don't have to, I mean, whatever we have to prove, we are going to suppose the opposite, its negation, and we will derive a contradiction. Integer n greater than 1 such that this for all a belonging to Cn, then in particular this will happen for a equal to pt also. So pt is equal to pt to the power n. So that is p to the power n times t to the power n, and that is equal to p square t times p to the power n minus 2 times t to the power n minus 1. Okay, this is m times this. Note that the smallest value of n being greater than 1 can have the smallest value 2. In that case, this is equal to 1, otherwise it is greater than 1. Whatever be the case, p to the power n minus 2 is a positive integer. Like that, t to the power n minus 1 is also a positive integer. So this thing is clearly greater than or equal to m, because it is m times some positive integer, which is a contradiction. And this pt is greater than or equal to m directly contradicts the fact that pt is actually less than m. So our supposition is wrong. That means such an n does not exist for Zn if m is not square free, and here the solution ends. (36) Let m and n be positive integers and let k be the least common multiple of m and n show that mz intersection mz is equal to kz. So that means k is the LCM of m and n. First, let x be an element in this. Then x is a multiple of k, and because k itself is a positive integer, so x being multiple of k means k divides x. But since m and n both divide k, we have this because the least common multiple of m and n after all is a multiple of both m and n. No, so m and n both of them divide k, so that's why they will also divide x, because k divides x. Thus x being divisible by m belongs to this, and also it belongs to NC, that is this is a subset of this intersection. Now we will prove the reverse inclusion. Now let y belong to this intersection. Then m and n both divide y, and so k divides y. This is the property of LCM, that the least common multiple of m and n divides any common multiple of m and n, and now y is a common multiple of m and n. Either you know this property from elementary number theory, or you can prove this very easily. Say you have these things given to you. What you do, you apply the division algorithm to divide y by k, because k is the LCM of positive integers m and n, so k itself is a positive integer that is non-zero. So you can divide y by k to get a quotient and a remainder, quotient q and a remainder r, where the remainder satisfies these inequalities, of course. Then using this and the minimal nature of k, you conclude somehow that r is equal to 0, and that will prove that k divides y. So it's a standard technique which we use in this type of situations. Anyway, I am assuming that this property is known to us, so we are just directly writing this. But this implies that y belongs to this subset, and hence the intersection is also a subset of this. Now you combine these two inclusions and conclude that the sets are equal. Next, 37. Explain why every subgroup of Cn is a subring is also a subring. Okay, is also a subring of Cn. Okay, what was the argument for this? I seem to not be able to remember it. If we take any subgroup of Cn, then it has to also be a subring. Does it have something to do with Cn being cyclic? Maybe. I can't seem to, for some reason I can't remember it. When I was writing these things down at that point, I thought that I have it in my mind, but right now I see it's not coming to me. Okay, so what we will do, we will leave it like this. In the next video we will solve it. Or this is a very easy thing. You may already know what it is. Anyway, we will continue with the solution in the next video, next Gallian ring video. So now what we do, we move on to the next one. Or should I think of it at least for a minute? Any subgroup is also at the same time a subring. In order to prove that a system is a subring, when it is already a subgroup, you just have to verify. Let's say your subgroup is H. Say H is a subgroup of this. Subgroup under addition, we have to mention, okay, it is written here, I forgot to write it. This under addition. So if H is a subgroup of Zm under addition, to prove that H is a subring, all you have to do is this. You take two elements in H, you prove that their product is again in H. Because the associative law for ring multiplication, that is true throughout Cm, so in particular that will be true for elements in H also. And the distributive laws are also true, just like that. So you just have to show that H is closed under multiplication. Now how does this follow from H being a subgroup? And this used to be something very easy. I totally forgot, actually, that's the problem. Anyway, let's not just dwell on this anymore. We will come back to it. Exercise 38 is C6a subring of C12. What kind of question is this? C6 is a subring of C12. C6 consists of, Okay. Truly speaking, Z6, the elements in Z6 are congruence classes modulo 6, and the elements in Z12 are congruence classes modulo 12. They contain entirely different types of elements. However, here in this book, we are not considering those groups. We are considering C6 to be this set consisting of ordinary integers. However, the operations are addition modulo 6 and multiplication modulo 6. So if Z6 has to be a ring, so if we are considering these things as ordinary integers, then it makes sense that one can ask whether Z6 is a subring of Z12, because in Z12 these are the elements. So at least this is a subset of Z12 in this sense. So for subring, we have to see whether, we have to see many things. You see, even before going through the axioms, you have to make sure that Z6, what I am trying to say is this: if you restrict, say, addition modulo 12, that operation on C6, then you get again things in C6. I think I don't see that happening. For example, under addition modulo 12, let us temporarily denote that operation with this symbol plus 12. 5 plus 5 is what? 10. However, under addition modulo 6, 5 plus 5 is again 10, but the modulus is 6, so that becomes 4. But if we just simply consider Z6 as a subset of this and then perform the addition modulo 12, that is the addition operation available in this ring, then we are getting something that is not in Z6. How can it be a subring? Okay, so we write the solution like this. Even when you consider these things, the elements in them as congruence classes, then also one can ask such a question. Even when Z6 literally is not a subset of Z12, considering its elements as congruence classes, then this question becomes like this: is there a subring of Z12, say S, that is isomorphic to Z6? That question will make sense. However, in the present form, our answer is no. Because C6 is not closed under addition modulo 12. This exercise is very confusing. confusing because if we are not considering this, say, isomorphic copies, what are we doing? Restricting the operation addition modulo 12 on Z6, fine, it takes us outside of Z6, but that restriction does not necessarily match with the addition of Z6. So how can it be a subring? But still I am saying, in spite of writing this solution, still I am saying that if you can come up with some interpretation of this exercise which makes sense without any ambiguity. This exercise, the way it stands now, is ambiguous. It can be interpreted like this, or it can be interpreted in a completely different way. So if you can come up with some unambiguous interpretation in which this is not the answer, it turns out that Z6 is a subring of Z12 in some very well defined sense, then please let me know. Okay, I don't see it being a subring. Then 39. Suppose that R is a ring with unity. Unity 1 and A is an element of R such that A square is equal to 1. Let S be a subset of R defined like this. The elements in S look like this: A R A, where R varies over the original ring R. Prove that S is a subring of R. Okay, does S contain one for two elements R1 and R2 belonging to R? We have A R1A, so this is any element in S, and A R2A, this is another arbitrary element in S. Using the elementary properties of a ring, this equals this. That is using all the distributive laws and everything, and this again has the form to be in S, so this belongs to S. Thus S is a subgroup of R under addition. Ideally, there is one more step even before these things, namely making sure that the subset S is non-empty. That, however, is very easy to see. That is because you take any element from R, say you take the identity, additive identity 0, so that shows that 0 is in S, so S is non-empty. But we don't write such things in the beginning if that is obvious. Okay, now also, now what happens when we multiply these two? Note that we then get R1 A square R2 A, and because A square is 1, let's just write that. So ultimately we are getting this. Now R1 R2 is again an element of the ring, so this belongs to S. Hence S is a subring of R. And we also have to answer this: does 1 belong to S? Yes, 1 belongs to S because because 1 is equal to, we can write from here itself, 1 is equal to A square, which can be written as A1A. So that's why 1 belongs to S. Let us do one more. Let this be the ring of all 2 by 2 matrices. Over the set of integers, and the author has written over the integers. He has a tendency to use words more than mathematical symbols. And let R be equal to matrices which look like this, where A and B are integers. Prove or disprove. it turns out that this is not a subring. Note that to show that we have to, actually what happens is that this is not closed under multiplication. So we take these two matrices, this is 1 and then do we have the required form. A and B are integers and these off diagonal entries in these matrices are their sum. -1 and 0 are integers and their sum is -1. So -1, -1. 1 and 2 are integers and their sum is 3. Yes. But what about their product? -1 -3 -4. -3 -2 is -5. -1 plus 0 is -1. -3 plus 0 is -3. And this does not belong to R because you see in the elements in R the off diagonal entries are equal. Here that is not happening. Okay, so R is not a subring of S. That completes this solution, and this also completes our today's video. We will continue from exercise 41 in the next Gallian ring upload, and we also have to come back to this, which I am still unable to, it's not coming to me at present, this exercise 37 and the 38th one, that also you please verify whether you can come up with some interpretation where Z6 becomes a subring of Z12. So that's it in this video. See you tomorrow with an analysis upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.